All right, didn't get an email to any questions in advance, but I do have a question in the chat. For Orgo Lab Part 2 next week, we're doing the melting point, TLC, and iron test. Yes, you are also doing your post-lab analysis, so everything has to be done before you leave the lab. That said, melting point, we have the rapid melting point devices now, so that takes you roughly a minute or two. It's going to take you longer to set it up than it is to actually run it. You're going to have TLC, shouldn't take you more than 10 minutes. The iron test shouldn't take you more than a couple minutes. It's going to take more time to get everything together than it is to actually conduct the test itself. So before you leave, you have to finish all the post-lab analysis, which means that you have to discuss what you found, your key results, percent yields, things like that. If you go to the course website under the lab practical, there is a link that says lab practical in the quizzes and assignments. That has the rubric. All that needs to be completed when you submit your lab notebook. Once you submit your lab notebook, you're done with the practical, and the grade you get is the grade you get. And the plan is to have your grades posted to the course website and to give you back your lab practical stuff when you come take the final exam. We are kind of in the home stretch here, so just kind of weird to think about it. Actually, 2 weeks from today is the start of final exams. So in terms of final exams, the time is posted to the course website. If you have questions, please email me to let me know. I will try to make sure that the rooms are also listed on there as well, and I need to double check. We actually have a special list that we get that tells us like more information about the exam times and locations. But again, that information will be on the announcements in the course website. Homeworks are all due when exams start. The big reason for this is just my sanity, so I can post all the homework grades. This goes for 152, 251, 252. All your homework assignments are due. I'll try to get those homeworks grade posted the first day of exam, so this way you can kind of see what you need in the course. Common question I get asked by a lot of students is melting points week. Yes, so it's that device. We have reference acetyl salicylic acid if you want to use it, so you can put the reference acetyl salicylic acid up there. You can do the melting point side by side and see if they melt at roughly the same temperature. With the rapid point, it does tend to be off for two reasons. One, your material is typically a finer crystallinity than the reference, so it's not going to melt at exactly the same point. And the second is there's just heat transport effects. So feel free to quickly ask some questions. One question you get asked is, how do I know what I need on the final exam? So let's say G here is your grade in the class. I mean, this is what's on Blackboard. So if you look at your current grade, wow, you can't quite see that. If you look at your grade on Blackboard, we'll make this number G. If you want an A in the course, take 90 minus your grade times 0.72, 0.78, and divide by 0.22. And that's what you would need to get on the final exam in order to get an A in the course. Now, the full caveat here, this is assuming all the grades have been posted. So if I haven't posted the homework or quiz grades, like that information is not going to be in there. But this will give you a really close approximation. For B, 80 minus your grade times 0.78 divided by 0.22. For C, 70 minus your grade times 0.78 divided by 0.22. I assume no one is shooting for like a D or F in this course, but that would just follow progression 60 and 50. I'll actually get an F, like just don't take it at all. If your grade times 0.78 is currently above a 70, that means you already have a C in the course. You don't need the final to pass the class. You need to do setup for melting point ourselves? No, I'll be there to help you out. The melting point, we just got the melting point apparatuses this semester, so I have directions written for the fall semesters. So for the fall semester, students will be obligated to conduct the melting point themselves. Also, with the melting point, we kind of have been inconsistently doing it because these melt temps we're using now showed up like a third of the way through the semester. Definitely future semesters will have a lot more experience with conducting the melting points. So for those of you who are doing the melting point in lab next week for the aspirin, I'll be there to tell you how to use it. Again, I know personally that you have not used these melting points a lot, so that's kind of unfair. Future versions of the lab manual actually have directions written on the back on how to use the melt temps. And yes, it was pressing numbers. You had to set it to function 1, which was temperature ramp. You had to set the target temperature, the target rate, and then, yeah, the old ones you probably have a lot of experience with. I'm not a huge fan of working with them because they are finicky. Sometimes you set them to 4, sometimes you set them to 5, sometimes you set them to 6. I also don't like that they're analog, so you're kind of like you're kind of having to read it while it goes along. And because they go so miserably slow, I've had a lot of students just straight up miss melting points because they got bored waiting for it and it came and went. With the wrapping melting points, you're talking about taking the measurement in 5 minutes. And especially with a reference in hand, that's actually a pretty good way to do it. You may not get the melting point precisely right because you're doing a rapid test, but because you're doing a rapid test in conjunction with a known, you can say pretty confidently that they're melting at the same points. And also with a lot of these materials, particularly what you're working with, the salicylic acid versus the acetylsalicylic acid, those do have radically different melting points. You can definitely tell the temperatures apart. This would not be true if they varied by like 10 degrees. If they varied by 10 degrees, I would say you'd want to get it about 90% of the way to the lower melting point, and then it has a slow melting point setting. It's literally 1 degree per minute. So if you want to measure, if your sample melts at 150 and you're starting at 25 degrees, you literally have to wait 2 hours and 5 minutes for it to get to 125. Again, the future lab manuals will have discussions on how to do this. Kind of unrealistic to expect y'all to be able to do that right now. The other big announcement for today. Um, there are no live streams. There are no office hours during exam week. Um, just by merit of the fact that, like y'all, my schedule changes for exams. So I am giving 3 finals, 1 on a Friday, 2 on the following Monday. I also have other things I need to take care of. I'm organic chemistry lead, so I'm in charge of setting the schedule for this fall. I need to make sure the lab manuals are set. I need to coordinate with my other faculty to make sure that they're ready to go for this fall. I also need to start prepping for my summer and fall courses. So there are no live streams, but if y'all are willing to coordinate with each other, meaning that you're willing to get a group of at least 3 together that want to do a live stream, let me know what times work best for y'all, and I'll see if I can fit that in my schedule. I mean that genuinely. I will see if I can try to fit it in my schedule. Generally, what I would do when we had in-person classes was that during exam weeks, I was physically on campus anyway. There's just things you have to do while exams are going on. And so what I would offer to students is that if you could organize a time when a group of y'all wanted to get together and do a review session, I could show up for an hour. And I'll make that a same agreement with y'all, is that if you can find a time where at least 3 of you want to get together and just ask questions, I'll set up a live stream where we can do that. It'll be recorded, it'll be posted to the website, so this way everyone can see it. The reason why I just don't hold these, oh, exam review session. Generally what I get when I do that is I get students who show up and basically just ask what's going to be on the final. I'm not going to answer questions like that. On top of that, if I set it up, I generally don't find students come prepared for review. They mostly come in hopes that someone will ask a question. When I make you organize it yourselves, there's more inclination there to kind of like want to come up with questions and come up with things to ask me, because again, you've only got the 1 hour. Now, that said, the ones who organize it, if a whole bunch of people show up, the ones who organize it get priority. So 3 students organize it and 20 people show up, those 3 students get to ask their questions first. I'm going to prioritize their question. It's kind of a reward for them, like taking that initiative. So again, unless I get an email saying like, hey, a bunch of us want to get together and go over material for the final, are you available on like these dates or times to do a live stream? If I get that email, I will send a link out to everyone so anyone can attend it. But definitely for those who organize it, and if I'm able to make it, you'll get priority in terms of getting your questions answered. And that's kind of it for anything I had to say today. Again, no email questions that I'm aware of. All right, if there are any questions, I'm just going to put the screen off so I can send a few emails. If you got questions, please feel free to bring them up in the chat. I'm definitely trying to answer your questions you have. Again, these are not lessons or lectures, these are office hours. All right, immediately got a question after I went to, so an aldol condensation is basic. Why is it different than aldol condensation in acidic conditions? Mostly the mechanism. So if we have So if we look at basic conditions, the basic is the easiest to catalyze and the one that makes the most sense. And we end up with a simpler way of generating these. Basically, the question is what's present. So in the case of basic conditions, we have hydroxide, which is really good at removing the proton, and that hydroxide kind of gives us the what we're looking for. For the acidic conditions, it's a little bit more complicated. So our first step is to protonate the ketone, which then gives rise to this intermolecular reaction. Here. And we end up generating the enol. So in this case, for the acid catalyzed aldol condensation, we actually go through an enol first. And then this lone pair here, or this double bond here, is what does the attacking. So in this case, we have our anion doing the attacking, and here we have the double bond doing the attacking. And it's just by merit that we can't generate an anion in a carbanion, an anionic carbon, in the presence of an H+, it would immediately take the hydrogen off. So what we do under acidic conditions is we use kind of like an acid-catalyzed tautomerization, and then we make the enol, and the enol is what does the attacking, whereas under base-catalyzed conditions, we end up forming the carbanion directly, and that's what does the attacking. Post-lab analysis is put in the lab notebook, is that right? Yes, so post-lab analysis definitely for this week and next week, that all goes into the lab notebook. And that's going to be what you turn to me at the end of the practical is your lab notebook, and that's what I'm going to grade. Now, as far as the dehydration goes, so let's say you run your aldol addition reaction. So we'll run this with itself, and we won't specify whether it's acid or base catalyzed. And we end up generating this, and the question is, why is it different under acidic or basic conditions? And again, it's just by what's available to do the reaction. So under acid catalyzed conditions, we don't have an OH minus to yank off that hydrogen, so what we have to do first is deprotonate, or not deprotonate. So we'll end up forming the hydronium. This will pop off. Make sure I can board space for this. Sorry, it's going to get really tiny. We form our carbocation, and then the water that comes off is going to pull the hydrogen off, and we're going to get acid-catalyzed dehydration. Under basic conditions, the hydroxide pulls the hydrogen off first. And once we pull the hydrogen off, we generate a lone pair, which comes down and forms a double bond, which kicks the OH off, and we end up getting this. Yes, you actually have 3 chambers in the melting point, so if you want to do the salicylic acid, the acetylsalicylic acid, and your compound all 3 at once, very easy to do that. In fact, I would actually kind of recommend you do that. Just go ahead and run all 3 so you can see how they compare. But yeah, as far as the acid and base, it's more of a question of fundamentally what ions can exist. Under acidic conditions, you have an excess of positive charges. If you have any negative charges, they're going to absorb those. So under acidic conditions, we can only run either neutral compounds or compounds with a positive charge. Under basic conditions, we can, because we have an excess of anions, we can run reactions, mechanisms that involve anions. Now, the base catalyzed is probably the easier to run, which I think is why we run a lot of base catalyzed aldol condensations, is by sheer merit of the fact that it's really easy to deprotonate that hydrogen. The acid catalyzed, you have to form the enols. Those aren't particularly stable, and you're asking to do a reaction across a double bond. Also not the easiest thing to do. So I think practically you can run an aldol condensation addition reaction under acidic or basic. It's just basic is more easier to do. Yeah, if you want to run all 3 separately, you're also free to do that. I mean, the rapid point measurements, the bigger thing that's just going to hold you up is waiting for the thing to cool down. And I say hold you up. I think those things will cool down in like 5 minutes has been my experience. So instead of doing like all three at once, you can do 3 over 20 or 30 minutes. It's all up to you. All up to you. Just let me know what you want to do when you go to run it. All right, you're welcome, Tia. And notice this is making sure if there's any electron withdrawing group, so if an electron withdrawing group is added, anything but ketone or aldehyde. Can it still go through Robinson action to decarboxylation through there as well? Yes. So decarboxylation is probably not as likely to occur. It looks like with the Michael reaction, you really need to have like basically carboxylic acids that are connected to the same carbon to make that happen. But as far as Robinson annulation goes, if you have so let's just say R here is whatever we're going to make and to make our whatever our Michael reagent is going to act on. And we'll start with just our very basic Michael reaction. So unless these are both OHs, I don't think you can do the decarboxylation reaction, but as far as this reaction occurring, as long as you have a base present, you'll kind of get that addition. Now, as far as whether or not you can do Robinson annulation, the Robinson annulation can occur because this ends up being an acidic hydrogen. So if we're able to form a 6-membered ring, we have 1, 2, 3, 4. Oh, I knew I was missing something. So we got our Michael addition. We have 1, 2, 3, 4, 5, 6. So we can form a 6-membered ring, but the question is whether or not we have the ability to lose hydrogens off of whatever carbon 1 is. So with the ketone, this is easy because we can resonance stabilize this with an enolate ion. So in the case of this, if we deprotonate, we can definitely resonate back and forth to give the enolate. Let's say this is a nitro group. So if we have a nitro group, this is electron withdrawing enough to kind of drive the Michael reaction, but the nitro group doesn't participate in any type of resonance with this carbon. So we form an anion here. There's nothing to resonance stabilize it, so this doesn't end up being a very acidic hydrogen. Same thing would be true if we had like a big sulfonic group. Even though we could, in principle, form a 6-membered ring, because we had nothing to stabilize this carbanion that we formed, there's no resonance structure here to help us out, we're probably not going to get the Robinson annulation. So again, decarboxylation, you need this to make that happen. But as far as like a Robinson annulation, unless you've got the ability to do like some type of resonance stabilization with that allylic carbon, you're not going to get Robinson annulation. Robinson annulation comes about from the fact that these are acidic hydrogens, and the base we use to drive this reaction is going to turn around and make this into a carbanion, which reacts with the Michael reagent to form the 6-membered ring. So why can't the nitro group go through Robinson annulation? So even though, so some people say that this is not a correct Lewis structure, it depends on who you talk to. This is one way of drawing the nitro group. The other way of drawing the nitro group is this way. Regardless, you need some way. So let's say you form this carbanion. If you try to form a double bond here, this carbon already has 4 things around it. So the only way to form a double bond here is to throw off the nitro group, which isn't going to happen. So even though the nitrogen may contain a lone pair, depending on how you draw this, it's too far away from this carbon to participate in any type of resonance. And the only way to kind of like move this lone pair is to break a carbon-nitrogen or carbon-hydrogen bond, neither of which is going to be particularly favorable. Now, if you had like what's a good way to do this? So let's say you have this structure, and if you don't mind, just work through page 40. I look back at the answer key, don't fully understand what's implying. Then I'm going to have to download. So if you look at this, if we form a carbanion here, this can engage in resonance to create a lone pair here. So we actually have a resonance stabilization here. So I guess the short answer is it will do Robinson annulation if there is some sort of double bond here, because then we can engage in resonance. But something like these, like if we just had 3 CF3 groups here, yeah, this would be really electron withdrawing, and that would promote the Michael reaction. But without a double bond to resonate with in order to like take the stress off of having a carbanion, it's just not acidic enough to make the reaction go. Okay. 252. Less. Okay, so page 40. Ah, yes. So, this is an interesting fact about fabric dyes. So let's just say I gave you a generic ketone and a generic alcohol. And what can happen here is we can form the hemiacetal. So this can attack, this can pull the hydrogen off, and we'll end up with the hemiacetal. Now, hemiacetals are stable, but they're only stable underneath like certain pH conditions, and I think it's only under highly acidic conditions are they stable. But if you start throwing like a base in there, you'll readily cleave this bond. So when you attach an azo dye like the ones that are drawn, and you've got these carbonyl groups, the only way to get them to stick to the surface of something like cellulose, which has a ton of OH groups on it, yeah, you can go look at the figures. The only way to get it to attach here is to form the hemiacetal. And this works fine if you're only ever under acidic conditions, but let's say you add a soap. Well, soap typically contains hydroxide ions, and that hydroxide ion is going to start breaking down these hemiacetals and making it come apart. So what it's trying to say is that the only way to get these azo dyes to attach to the surface of the cellulose is to form a hemiacetal. Oh, only under stable under basic conditions. So if we expose it to like a weak acid, sorry, I got it backwards. If you expose it to a weak acid, which is not uncommon, like your body is just naturally acidic, you're going to start breaking down the fabric dyes. And this is actually kind of an issue with fabric dye in general, is how do you make dyes fast? Meaning, how do you keep them from coming off or fading? Things like bleach will, bleach will actually begin to oxidize these to the point that they can't stick to the surface anymore, or they'll break down the dye. But just generally washing your clothes, once your sweat breaks down the dye and kind of breaks that fabric dye out, then you're just going to wash the dyes away. So yeah, this is kind of like a big problem with fabric dye manufacturing, is like, okay, you've created this very pretty dye. How do you attach it to a surface, and how do you attach it to a surface in such a way that it doesn't come back off pretty readily? And if you're curious, you can go take a class on polymer and color chemistry. Like, it is a whole other field well outside my expertise. And there are definitely better functional groups you can attach with, but again, you're still looking at like ester and ether chemistries. Anything that will decompose in ester and ether will probably decompose a fabric dye. Hey, you're welcome. You can do 3-ethyl groups. The question is, for Hoffman elimination, do you need to do 3-methyl, or can you do 3-ethyl? You can do the 3-ethyl. The reason why the 3-ethyl would make it a better leaving group, but the 3-ethyl would also be the reason why that reaction would be hard to drive. So let's say we have our NH2 group, and we have our big material, and we want to run, instead of CH3R, we just do RI. And we run the reaction in excess. And before we make our nitrogen depart, this would be our structure. We'd have the 3 R's on it to give the diazonium equivalent. Well, the problem is that if R is really big groups, they're probably not likely to form. There's just no space for them to occupy. So yes, you could do it with ethyl. Methyl is going to be better because methyl isn't going to kind of like, the methyl groups are going to push away other methyl groups. I mean, they are, but not to the extent like an ethyl or a propyl or a tertbutyl or anything like that would do. I really want to quote Wall Street Bets to you, and I can't. But go look up what they say you should never go full on for. I think it's also a reference to Tropic Thunder. But anyway, R, yes, you can do ethyl, but the methyl groups are less sterically hindered, so they're much more likely to react and complete the reaction. Still be possible, yes, and this is a major problem with amine halide chemistry, is like, it'll keep reacting with all the halides. You'd have a lot of trouble controlling that type of chemistry, and off the top of my head, I don't know why you would want to do anything like that. But yeah, in principle, if the R's were ethyl, methyl, and propyl, and then you do the silver 2-ox or Ag2O, it would still work. But it'd just be a lot more difficult to run. You're welcome. Can you do a problem on Robinson annulation? Sure, we can just pick a generic one. And again, we're just going to kind of keep these symmetric. When you do Robinson, when you have asymmetric microreagents, you can create a lot of problems for yourself in terms of the number of different products that can be formed. So the first thing we always go through is the Michael addition. Again, we're going to form a carbanion. It's going to add as far away from that ketone. It's going to add far away from that ketone. Oh boy. Okay. So in order to work out the Robinson annulation, what I found works best is to number the carbons. And what you want to do is you want to start with an allylic carbon on the thing that was attacked by the microreagent. Now, in principle, we could also do this with the microreagent because we have these groups here that are still acidic. The bigger reason why we get attack on this versus attack on this, because these are adjacent to each other, they're more positive, so they're more likely to react. So we want to form a 6-membered ring. If we start here, we get 1, 2, 3, 4. That's not a 6-membered ring. So we're going to start further away. So we have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. And because it's symmetric, it doesn't matter which way you go, so we'll make this carbon 6. Now, a symptom of a Robinson annulation is this 6-membered ring. And so we'll number our carbons. 1, 2, 3, 4, 5, 6. And now what we've done is we connected carbon 1 to carbon 6. So this line here is this bond here. So now we look at what's along each carbon. Carbon 2 has a ketone. Carbon 3 is by itself. Carbon 4 has 2 methyl groups hanging out of it. Carbon 5 has this ester branch, or ketone branch. And this one we attach carbon 1 to carbon 6. That breaks open our ketone. And we have a methyl group hanging off. So now that's your Robinson annulation. The question is, does it do a subsequent elimination? Well, we have to answer that question. We need to see if there's any hydrogens on this carbon 1. If there is a hydrogen on this carbon 1, it's available for elimination. When our discussion boards due? They are due at the start of final exams. So it's due at the same time as homeworks. All right, so because we have a hydrogen here, we can do our elimination. And that's your elimination product. Now let's say 1 here was actually a dimethyl. So before we did the elimination, we'd have 2 carbons here. In this case, we can't do the elimination here. It's not going to do us any good because there's no hydrogens to eliminate. But you could do elimination back to this bond here. That would still give you the alpha-beta conjugation. But again, we're going to focus more on ones where you can do, like you can kind of pick up the pattern a little bit easier. We're going to do, if we are going to do elimination, it's going to be between carbon 6 and 1. My coworker and I were actually discussing this week, I think Monday, we were in lab at the same time. And we talked about how in our undergraduate courses, Grignards were like the thing. That's all we talked about were Grignard reagents. And it was weird because he said he was actually a practicing organic chemist, and he went to Roche Chemical, and like they were like, we do not do any Grignard chemistry. And they started talking about all the carbonyl chemistry he was going to be doing, and like platinum chemistry he would be doing with organic compounds. And he thought it was weird because he'd spent all this time in college learning about Grignards and never used them. To be honest with you, I'm kind of proud of y'all for organic too, that you're not asking me incessant Grignard questions because it's become such a minority part of the course. The questions you're asking right now are actually industrially relevant questions. So like, how do you do these types of like ring forming mechanisms? How do you do carbon-carbon coupling without working without an organometallic reagent? This is actually putting you on really solid footing. I realize most of you will never go on to be chemists. That's fine. But it is refreshing to see you not like focusing on really esoteric chemistry reactions. Everything you're talking about here, the questions you've been asking, are actually more relevant to like what's done in practice in the real world. So good for y'all. slide 106. I'm going to have to download that one too, because I don't have my flash drive on this computer today. Yes, it should be ortho, not meta. That's just a typo. Aldol addition. I'm not sure your contents of your question. So for aldol addition, that's when you end up with the ketone and the alcohol, and then for the aldol condensation, that's when you get the ketone, the alpha beta unsaturated. So we'll really simplify it. If this is in your structure, this is the aldol addition. If you end up getting the double bonds next to each other, that's the aldol condensation. Should you be heavily stressed for exam 4? I would say it's no more difficult than exam 3. I would not panic. So on our end as instructors, we want to make sure you understand the concept. We also want our test examples to be really straightforward. And because of this, we're kind of in a weird position when we start doing practice problems. So with aldol addition condensation, it is very, very easy to take what is a very simple problem and make it insanely hard. And to give you an example of this, when I was in grad school, we had to solve differential equations, and you get some instructors like, well, I'll change a positive to a negative. What's the harm? And it ends up being like some obscure 1963 Russian special function that solves it. So what looks like a really simple example generally isn't. And Sorry about that. Laptop died on me. And apparently it took 2 restarts to get it going again. So let's make sure it's actually up and running. There we are. Yes, laptop died on me. I went to reboot it and it died again. I'm really curious how this is going to work this summer when I'm doing this like 4 days a week. They're also sadists. To everyone's scared. You got cut off. It's frozen. Anyone else lose a stream? Yep. Yes. Keeps freezing. RIP. Do we have a question about final exam prep? Will there be a final exam study? Provided like last packet study like summer. I'll need to check. I don't remember if I actually have one for this course. Oh, actually there won't be, but I will get it. Like what we talk next week. I'll talk about what you need to emphasize in terms of what you're studying for final and what old package you can go back to and like get some help with on that. Let's take a look. I got the exam up in front of me right now. Let's see. Straightforward, straightforward. 5 might be a little tricky. Synthesis. If you've done the discussion boards, the synthesis is really easy. If you've done the discussion boards, the synthesis is really easy. The free response synthesis. I know one of you is going to get the free. I know several of you are going to get the some of the syntheses very easily. Yeah, I really wouldn't be that worried. Oops, forgot to take that comment out of the questions. For number 10, there's going to be a weird comment that was actually an editing comment to myself. It doesn't affect your answer, but if you're curious why it is what it is, it was an editing comment to myself. Amine naming. So we're going to keep it pretty simple with the alkyl branches. We're not going to focus on too many substitutions. So when you have an amine, you have a primary, secondary, tertiary. If you have a secondary, there should be an N. If you have a tertiary, there should be 2 N's. And I believe it's by chain length. So you start naming it by successively longer chains. Let me bring up the notes really quick just to make sure I'm telling you that right. Yes, it is by the length. What makes you think a student stands out as extraordinary? I don't have a metric for that question. Um, but anyway, amine naming. So we're always going to do shortest to longest. We should always have a YL in there for the branch, and it's always going to be a mean. Or amine. And if we have more than one, well, then we use the di and the tri. Thought the amine naming was slightly weird. I don't know. But yes, can you also review? So if we have primary amines, we would just name the branches as they were. So this would be like a methylamine, ethylamine, isopropyl, or 1-methyl, ethyl. Your typical naming of alkyl branches. If we have two, we do them by link, so it would be N-methyl, ethyl, amine, or if we start branching them out, we would do two. If we have two, we do N-dimethyl. We would do dimethyl. Products for chemical alkene differ based on reaction conditions. How would we see that? It would be given to you. So for potassium pentanganate, if you see it says low temperature, low concentrations, it forms the diol. If you see high temperature, high concentrations, that forms the ketones or aldehydes. Excuse me. Now, if we have three, this would be methyl ethyl N-methyl ethyl propylamine. And again, we're going to keep it really simple with these. We're not going to get into really complicated amines. Twofold for this. One, you start getting like wrapped up in details. Hey. Second problem is that we're starting to get kind of into organic reaction or biomolecules. There's a different set of namings for those. There you go. You should go back to sleep. You're welcome. But yeah, looking through test 4, I would say if you've done the discussion boards, you should be able to get at least a 50 on this exam pretty trivially. Six is not worded properly, but I think you can probably infer what it means. 5 is also worded incorrectly. Yeah, this is a really straightforward final exam. Four, you should be able to figure out for the synthesis. 3, I know one of you is going to get it. 1, I'd be interested to see what I wrote for the key. Talking about exam 4. So exam 4 is really straightforward, in my opinion. Again, if you've done the discussion boards, you are more than set for half the exam. Yeah, if you look at the question, like it's worded weirdly, you can tell I picked a different direction with the question before I wrote it. You'll be able to infer. You don't have to look at the question. You don't have to look at the words to know what the question's asking. It's just worded weirdly. Like it looked like I was asking you to reverse engineer, and then like the question is like not asking you to reverse engineer. It's just asking you what's the product of a reaction. So I must have changed my mind halfway through writing the problem, like as to which way to go. But it's kind of the problem. They wanted all our exams at the start of the semester, so I had to write all of them at the start of the semester. Now I have like the benefit of hindsight to look at them. Yes, and I would definitely say you do not need to focus your efforts on the last chapter material. Um, there's a reason why we're not going to work on it for very long. It's biomolecules. Straightforward, correct. Yes. So, really no surprises on this exam. Again, if you've been doing the discussion boards, a lot of this is going to look familiar to you. All right, you're welcome. You about ready to be put down? No, not yet. All right. See y'all next week. All right. Thanks for coming, and I will talk to y'all. See some of y'all tomorrow, and definitely see a lot of you next week.